operation on the memory to decode the ciphertext. Now you're doing a number of variable operations which can change with every encoder, and this makes it considerably harder to fingerprint because you're not just doing the same thing over and over with different instructions. The last one that will be discussed is ADM Mutate. It was released as essentially a small toolkit. It had, I believe, encoders for 3 architectures, though only the IA32 one was actually polymorphic. It had lots of NOP codes included, or NOP opcodes included for also 3 architectures, IA32, Spark, and HPPA. And like Shikata-Ganai, it also uses a 4-byte XOR key. So let's look at the way that Shikata-Ganai actually works in generating the code. It has programmed-in logic, which has a dependency chain. So basically, if you look on this graph, if you look at the top left, there is a box with a FPU inst written on it, and that's FPU instruction. And it has a little pointer to a little box saying FNSTN, which is also another FPU instruction on the IA32 architecture. But what this graph essentially means is before FNSTN can run, FPU inst has to run. And before pop EBX can run, FNSTN must be able to run, or must have run. And for loop block, pop EBX, mov Zorlin, and mov Zorkey must all have run before you can even get to the loop block. So this is just an idea of how these encoders actually achieve random ordering, because as you can see, nothing depends on clear ECX, FPU inst, and mov Zorkey. So either one of those can be the first instruction. So this basically allows the encoder to randomly put in instructions in random places by putting dependency chains, because this instruction depends on this instruction running beforehand, and this instruction depends on this instruction running beforehand. So there are 3 possibilities for the first instruction, either FPU inst, clear ECX, and mov Zorkey, and these are dynamically generated so that it changes every time. So for an example of the way the runtime works is a random opcode is chosen that can be run. In this case, it's 3, and in this case, it was a FPU inst. So that's the first byte of the shellcode, and then the second instruction is chosen clear ECX. So that's the second instruction, and it just generates this in just random order, and it can create large numbers of permutations because it doesn't have to be in this order, and it also doesn't have to use these same instructions. Going back to the 3 rules of polymorphism, what it's doing here is this dependency chain allows you to reorder it in different ways every time. It also uses different instructions every time, so if you look at the same code generated 2 times, it looks nothing alike. It has different orderings and it uses different instructions. So it's pretty hard to tell that it's actually the same thing. And to an IDS or to some packet filter, it has no idea what's going on. So this is just the code continuing. And this is just a diagram of assembly dumps of 2 Shikata-Ganai encoders. So if you look at them, they're of the same size, but they don't really look that much alike. And so what are the weaknesses in this? If you look at the 3 rules of polymorphism, it has some weaknesses based on its implementation. For rule 1, the many permutations are made for every single instruction. Well, some instructions have few or no permutations. For example, FNSTN, one of the instructions, is always there in every single shellcode. And it's the same 4-byte sequence, so this could be an indicator that the Shikata-Ganai is in that packet stream if an IDS is looking at it. The other thing is it always uses sub or XOR ECX to clear the ECX register, and then always uses the same instruction to move something into that register. That instruction chain also has very few possible permutations on it, which makes it weaker to analysis. The other thing is that ECX is always used as the loop counter during the decoder loop, and the get EIP and looping methods can have more possible permutations. For example, they always use the loop instruction to loop, and they always use the FPU FNSTN instruction to get EIP. there are more possible permutations of this than just that. The weaknesses in rule number 2, random ordering instructions, there are none. It's done where possible and it's done properly. The weaknesses in rule number 3, random not padding is added in. Well, random not padding is actually not added in anywhere. Rule number 3 is totally ignored by this encoder. So if we wanted to, I mean, there are some static instructions or some instructions that are very few permutations. So we could build a very basic fingerprint, and I'm using snort as the example here. So that first line you see, the content line in the center, is a basic fingerprint for the FNST end of instruction. Like I said, the FNST end of instruction is present in every single encoder of Shikata Ganai. So this is a very good way to find if Shikata is likely to be in that stream, because if the byte sequence isn't there, then Shikata isn't in that stream. Furthermore, we can look at some other things going on. That second line is a Perl regular expression, and what it finds is the clear ECX code. If you look here, you can see the clear ECX box, and it only has 4 possible permutations. So we use a Perl regular expression to be able to find every single one. The third line is a Perl regular expression that can just catch the ordering of one of the blocks of code. There are very few permutations for the FPU ins instruction. Then it fingerprints an FNST end instruction. Then it fingerprints a pop EBX instruction. And basically what this is doing is essentially the encoder was not built with many permutations in it, so you can build Perl regular expressions to actually find these, because there are just so few permutations that a Perl regular is powerful enough to be able to match all instances. However, it's still a fairly weak fingerprint, and many false positives can occur on this because it just doesn't fingerprint on that much data. So is it possible to be more accurate, because this just doesn't really provide us with much? And the answer comes in looking at byte distribution. And basically, few permutations are possible for most instructions, and each byte offset in the encoder has a limited number of possibilities. Well, what does that actually mean? The first instruction in the entire encoder can only be FPU ints, MOV Zorlan, or clear ECX. It only has 3 possibilities. And of those 3 possibilities, each one only has a few possible permutations. So we know that the first byte of the encoder is going to be one of the first bytes of those instructions. Basically, in case you're still confused, it just means that certain byte offsets can only have certain instructions, because the encoder has very few possible permutations for many of these instructions. And as you can see on the line below, that's a Perl regular expression for the first byte. The first byte can only consist of those characters, 29, 2b, 31, 33, hexadecimal, etc. Those are the only possible permutations for the first byte. And now the question is, can we do this for each byte? I mean, is this really going to give us a lot more capability to fingerprint this? Because if this is the only one that has, let me state this in a more clear fashion. Now the question is, can we do this for each byte offset in the encoder? We know that these byte offsets have only a limited possible amount of permutations to occur in each byte offset. So the question is, can we do this for each one and actually have a small amount of results? Or is each byte offset in the permutation, or is each byte offset in the encoder, I'm sorry, likely to have a bunch of possible instructions, which doesn't really narrow anything down? To look at this, I built a small program which I've encoded in the code.tar.gz file for this presentation. And it's essentially a polymorphic encoder analyzer. It's just a very simple program. To input it, or the input is a large set of polymorphic encoders. So, for example, if I Shikata Ganai, what you do is you get tens of thousands of possible permutations of this encoder, and you just put them all in a file. And so what you can do with this is you can look at every single byte in every single one of those encoders, and you can say only these bytes actually occurred in all 20,000 or 50,000 encoders. So it's statistically probable that these are the only ones that are going to occur in the entire code. encoder anytime. To restate that, basically, you look at a large number of these encoders, and if the you look at a large number of encoders, and it's likely that if you have a large enough set, that the first byte of all of those encoders are the only bytes that are going to happen for the first byte, and the second byte of all of those encoders is the only second byte that are going to happen for all those encoders. So what can you output if you have this large set of permutations? Well, you can output the static bytes occurring in every single encoder because, sorry, there's a train moving through. All right, so what if you have a large set of these polymorphic encoders? What can you really glean from this? Well, you can look at every single one and you can figure out the static bytes occurring in every single one. You can also the PCREs, or the Perl regular expressions, as I did here, that one down below, for every single byte offset. You can essentially look at the byte distribution. You can look at the bytes that are going to happen at every single byte offset in the encoder. You can also do spectrum analysis, which is something I'm not going to discuss because it's not really that useful for actually fingerprinting shellcodes and having it be consistent. But if you look down below, I'm sorry you guys can't see that, but it's just the dot spectrum program being run with the options SBP, which means size, static bytes, and PCRE, or per regular expression, on a file called Shikata MSF2 L1024, which means that it's the Shikata Ganai file or it's a bunch of Shikata Ganai encoders in Metasploit Framework 2 that are less than 1024 bytes. And what it says is basically, I have 20,000 of these encoders, and it says there's a static sequence of D97424F4, which is the FNSTN we fingerprinted here in that content statement. And it outputs a gigantic Perl regular expression. And what this Perl regular expression is it represents every single possible byte that can occur at every single byte offset of that encoder. Now, in some of these, there are many, many possible combinations. For the second byte, you can any character but 0 and 255. But for some of these, it can only be two combinations, like the third line there to the right. It's the only possible combinations are hexadecimal 31 and hexadecimal 83. There are only two possible combinations. So this narrows the fingerprint down considerably because now we can we have something that fingerprints the entire encoder based on the byte distribution of it. And so this is just a large, ugly snort fingerprint, which fingerprints the Metasploit Framework 2 version of Shikata Ganai, which are less than 1024 bytes. And if you can see it, the first 3 bytes are just the static bytes or the bytes with few possible permutations, and the last line is a Perl regular expression for the byte distribution, which should narrow it down so considerably that there are few to no false positives anymore on this fingerprint. Because without that byte distribution information, there's going to be false positives all over the place because that's just not a very good signature just by itself. And so just a little on this fingerprint in case you guys are planning to drop it in. The Shikata Ganai signatures change between Metasploit 2 and 3. It also changes if the payload or if the actual shellcode the encoder is encoding is less than or greater than 1024 bytes. So if you guys plan